This is slide number 53 and I am your presenter Asloob Mudassar. We have discussed earlier two cases. The first case in which the object was just behind the lens. In the second case the object was at a distance d in front of the lens. And now the third case we are going to discuss is the case in which the input field, in which the input object is behind the lens. For example, in this figure we have three planes: xy plane, zeta eta plane, uv plane. The three planes are parallel to each other. The lens is placed at the xy plane, the input object is placed at the zeta eta plane, and the field will be calculated at the uv plane, which is referred to as the Fourier plane. You can see that the distance between the object and the Fourier plane is d, and the Fourier plane is located at the back focal plane, of the lens at a distance f behind it. The three planes pierces the z-axis perpendicularly, and the optic axis is along the z-axis. That is all the three components, that is the input, that is the thin convex lens, input object and the Fourier plane, they are centered at the z plane or the optic axis. So you see that below we have the caption, that is the optical system indicating a lens plane, input object plane and the Fourier plane. So let's read the statement. The three planes, lens plane, input object plane and the Fourier plane, are indicated in the figure along with the coordinate axes x, y, zeta, eta, u, v. All the planes are parallel to each other and pierces the z-axis perpendicularly. The input object plane is at a distance d from the Fourier plane, whereas the Fourier plane is at the back focal plane of the thin convex lens. Let's assume that the lens is illuminated normally with a plane wave of amplitude equal to a. Since we are illuminating the object, we are illuminating the lens, the input lens, for example, normally, it means that we can drop the constant phase vector that the input plane wave will carry. So dropping the constant phase vector with the plane wave, the field just after the lens is. So you see that the field input the lens is a plane wave which is having amplitude equal to a and having ignored or dropped off constant phase vector. So you see that now the field just after the lens, the field just before the lens is ul of x, y, which we can regard it as ul of x, y is equal to a. Because here you know that in equation number 44 on the right hand side we have dropped the constant phase factor due to the plane wave. The field just after the lens, which we are denoting it by ul prime as a function of xy, is given by. So you see that you can see that ul prime on the left hand side is equal to the pupil function p of xy multiplied by the phase transmittance of the object, which is e to the power minus iota k over 2f multiplied by x square plus y square and multiplied by ul at x, y. Ul is the input field which will pass through the lens and will be affected by the phase transmittance of the object which is given, and also by the dimensions of the pupil function of the lens. So you see that putting the value of ul from the previous equation, that is from equation number 44, the equation number 45 takes its final form in this second step, which is equal to a into p of x, y, e to the power minus iota k over 2f, and within the parentheses we have x square plus y square, because we are still on the xy plane. So all these parameters carry the x and y variables. So let's represent the field just before the input object by u naught of zeta and eta. So you see that this field is very important, u naught of zeta and eta. Actually this is the field which is just behind this input object plane. So over here at the zeta eta plane we have this field which is referred to as the u naught of zeta and eta, and you know that we have calculated the field which is ul prime just after the lens. We have to propagate this field up to the distance which is the distance between the lens and the object, and that distance is f minus d. from the figure you can see that the distance between the lens and the input object is f minus d. So we have to propagate the field after the lens to travel a distance equal to f minus d to reach at the input plane. Okay. So let's represent the field just before the input object by u naught of zeta and eta. Let's connect the two fields, one just after the lens and the other just before the object, through the Fresnel formula in terms of the Fresnel transfer function. So you see that we have to apply the Fresnel formula in order to calculate the field in the free space propagation, in the free space that is after the lens and just before the object. So for that one we are using the Fresnel transfer function approach. So which is given in equation number 46. You see that we have the Fourier transform of the field just after the lens, that is the Fourier operator operating on the curly bracket, and within that one we have the field just after lens, which is the ul prime of x comma y. And you know that this field is multiplied by the capital K of x comma y, which is the Fresnel transfer function. And you know that both these are being multiplied within the curly bracket, and on that one the inverse Fourier transform operator will operate and will give you the field at the input object, which is u naught of zeta and comma eta. So you see that we have in the second step we have substituted the values of capital K of fx comma fy, and you know that you can see that we have put the distance as f minus d. So f minus d is the distance through which the transfer function will help us to find out the field after traveling this distance. So we have the transfer function e to the power minus iota pi lambda. Within the parenthesis we have f minus d, and multiplied by the Fourier variables, which is fx square plus fy square, and of course at the end we have to calculate the Fourier transform of the field after the lens. And once we have calculated the Fourier transform, we have to multiply it because the Fourier transform variables will be fx and fy variables. So these two transfer, so it will be multiplied by the transfer function. Then the inverse Fourier transform will be taken, which will give us back the fx, the Fourier frequencies fx and fy will be converted back into space variables x and y, and those space variables x and y will be at the end will be converted to zeta and eta coordinates, because here we are dealing with a zeta and eta plane. And you know that on the left hand side we have u naught of zeta and eta, so all the variables at the end on the right hand side of equation number 46 should contain zeta and eta and not x and y. Okay, you see that where f minus d is the separation between the lens plane and the input object plane. Now let's calculate the Fourier transform within this this curly bracket, which is the Fourier transform operator operating on ul prime x comma y, which is also given in equation number 47 on the left hand side, and we on the right hand side we have substituted the value of this field from the one of the previous equation. So the Fourier operator is operating on the curly bracket that contains a into p of x comma y e to the power minus iota k over 2f. Within the bracket we have x square plus y square. So you see that now this Fourier operator we are not operating Fourier operator on the pupil function, because here we are assuming that the pupil function we are taking it as a constant, and we also know that the Fourier transform operator will not modify the pupil function, the Fourier optics has no ability to modify the pupil function by the Fourier transform operator. So this pupil function is taken out of the Fourier transform operator as a function of x and y, and we shall later on address the pupil function in detail. So we have so the Fourier transform operator has operated on the exponential part, which contains x and y, and you know that we have the Fourier operator operating on the curly bracket in equation number 47 in the second step, e to the operating on e to the power minus iota k over 2f and x square plus y square. So peak of x has been considered independent of x and y as far as the lens pupil function is considered. So you see that after explaining equation number 47, we are now going to take the Fourier transform of the term given in equation number 47. So let's take the Fourier transform of this quantity. But you know that here we have to multiply. Okay, so you see that we have given the full description, but you know that in equation number 47 which we have written, we have actually written equation number 47, the full equation number 47, but you know that here we are doing some trick over here, that is we are multiplying in the first step by lambda f over iota, and you know that we are also multiplying it by iota over lambda f, so that there should be no difference by the multiplication of these two factors. And you know that in the exponent we have converted that one also by substituting the value of k by 2 pi over lambda, and then we have rearranged the terms so that we can have again iota over lambda f within the exponent as a power of the exponent multiplied by x square plus y square, and also multiplied by minus pi. So this is why we have done is that so that we can generalize the calculation of the Fourier transform operating on this exponent part. So you see that I am introducing the parameter n square over here. So within the bracket, within the curly bracket, iota over lambda f will be represented by n square, and similarly we have this some term outside this Fourier operator will also be converted into n square, and you know that n other same factor but in the reciprocal form will be converted into 1 over n square. So you know that in the Fourier operator now we have Fourier operator operating within the curly bracket, and in the curly bracket we have n square into e to the power minus pi n square x square plus y square. So you see that this is quite this is a familiar term for which we have already been calculating the Fourier transform. So we are now directly writing the Fourier transform of this quantity in the next step, which is e to the power minus pi over n square, and within the parenthesis we have we have fx square plus fy square. So you see that we immediately wrote down the Fourier transform of the from the previous expression, and you know that we have 1 over n square which was already before the curly bracket on which the Fourier operator was operating. Now you know that we are substituting back the values of n square, which is equal to iota over lambda f. So substituting these value backward, and we have in equation number 48, the last step will give you the Fourier transform of the field which is ul prime of x comma y. And you know that this will give you the field. This is the Fourier transform of the field which we are addressing over here, you know. For example, in this equation, in equation number 46, we need to calculate the Fourier transform of ul prime of x comma y, which was the field just after the lens, and we have calculated that one in equation number 48 in the last step of equation number 48. Now we are going to substitute these values, but using equation 48 into equation number 46. We have equation number 48, and we are going to substitute in equation number 46, so that we have to calculate the field on the left, which is u naught of zeta and eta, that is the field just before the input object. So this field will be calculated after substituting. So we have made the substitutions over there in that equation. So we have replaced the parameters over there, but you know that when we substitute these value over here, we have another parameter which is the Fourier transform inverse operator. But you know that these operators will help us, but you know that when we calculated the Fourier transform, for example this quantity, then you know that when we multiplying this quantity over there, this factor which is e to the power plus iota pi lambda f into fx square plus fy square will be cancelling a part of the exponential which is appearing over there. So you see that e to the power minus iota pi lambda, within the bracket we have f minus z multiplied by fx square plus fy square. So one of these parameter will be cancelled out by substituting the value of the this value which we calculated from equation number 48. So after calculating one of the exponent, now this Fourier operator which is at the end of this one, including the curly brackets coordinates of these one, we are substituting this Fourier operator over there. So you see that now we are left only one terms, which is d terms, which is the d dependent terms, because here we have f minus d. The f terms will be cancelled out by the terms which is contained in the Fourier transform of the field. So you see that we are left only the term which contains d, as you have seen in equation number 47. In equation number 48. So you need that. So you see that in equation number in equation number 49, you have in the first step, you can see that we have a Fourier inverse operator operating on the curly bracket, which contains e to the power plus iota pi lambda d, and within the bracket we have fx square plus fy square. So we need to calculate the inverse Fourier transform of that one. For this we are again are going to introduce some parameter. Here the parameter is m square, and you know that m square as listed below is m square is equal to iota pi, iota lambda and d. So we are substituting this term over in the as 1 over m square, and the same m square is introduced inside the curly bracket, and you know that in the exponent we are also replacing the term by m square. So we have this very systematic thing that we can immediately write down the inverse Fourier transform of the quantity in curly bracket, which is given in the last step in equation number 49. So you see that the inverse Fourier transform is e to the power plus pi into 1 over m square into x square plus y square. So you see that now we have all the terms containing x and y, and you know that we have to put back the value of m square, which we have done in the next step. In equation number 50, we have substituted the value of m square back, and then you know that in the first step we have all these terms with their original values after substituting the value of m square. Now you know that we have to execute, that is, we have to put the value x replaced by zeta and y replaced by eta, so that we can calculate the field in their right coordinates. And you know that in the equation number 50, in the second step, we have a multiplied by f over d. In the pupil function, we have left the arguments as blank arguments, because you see that x, y cannot be substituted over here, and nor we can substitute zeta and eta, because we have to calculate this pupil function, because this pupil function, the size of this pupil function cannot be controlled by the Fourier optics, by the application of the Fourier optics. So we shall address this after in the next slide, or maybe immediately after equation number 50. But you know that we have replaced x square and eta square in the exponent, which is now e to the power minus iota k over 2d, and we have within the parentheses zeta square plus eta square. Okay, now we have to, if we could address p, the pupil function, with its right coordinates, then equation number 50 will be complete. So this is the field, you know that u of zeta and eta is the field just before the object, that is just before the input object, which and the input object, you know that where the object was plane is the zeta and eta plane, which was obtained from the field ul prime of x comma y, which was the field just after the lens. The two planes were separated by a distance f minus d. We could also obtain equation number 50 from equation number 45 by using the following transformations. So you see that in this transformation, the amplitude will be transformed as a into f over d, x variable will be transformed as zeta into f over d, y variable will be transformed as eta into f over d, x square will be transformed as zeta square into f over d, y square will be transformed as eta square into f over d. That is, f over d is a scaling factor. So where f of d is a scaling factor, which can also be found from the geometry shown in the next slide or in the next page. For example, look at this diagram. Here we have shown array in the dotted line. Two dotted lines are shown. One is along the optic axis or the z axis. The other one is touching the lens axis, the lens point, the far end of the lens point, and also the far end of the and passing through some portion of the object, and also meeting the UV plane or the Fourier plane at the z axis. So you see that we have actually two right angle triangles. One, the base of one right angle triangle is equal to f variable. The other is the other right angle triangle has a base equal to d. And you know that this one right angle triangles which has the base equal to f has two right angle perpendiculars. One is x, the other is y. And similarly for the shorter triangle which contains d as its base contains two perpendiculars. For this triangle both are at 90 degree to the z axis. One is the zeta axis, the other is the eta axis. So using the two congruent right angles triangles, we can immediately write that x over zeta is equal to f over d, and similarly y over eta is equal to f over d as given in equation number 51. Now you know that we have to find out the value of x and y. So finding out the value of x, y and substituting in the pupil function over here, that is the pupil function where we have left these terms as blank, we are going to replace the arguments of the pupil function by the arguments of x and y, but those have been calculated using equation 15 number 51 and not by the Fourier optics. So we have you know that this is the pupil function in equation number 52 where we have plugged in the original values that we have calculated using the above geometry, and the total field just before the input object now becomes u of zeta and eta is equal to a into f over d multiplied by the pupil function with the coordinates zeta into f over d comma eta into f over d, and then we are multiplying e to the power minus iota and k over 2d multiplied by zeta square plus eta square. So this is equation number 52. And you know that all the variables on the right hand side now contain zeta and eta. Using the Fourier tools, it is not possible to find exact size of apertures. As the wave propagates, the size of apertures can only be found through the geometrical optics approach or simply through ray diagrams. Assume that the amplitude transmittance of the input object represented by Ta of zeta and eta. So this is the amplitude transmittance of the input object which was placed at the zeta eta plane. And before that we have calculated the field which was u naught of zeta and eta. So this is the field that we have calculated just before that object, and the amplitude transmittance of that object is Ta of zeta and eta. The field just after the object which is u naught prime of zeta and eta can be found as given below. So u naught prime of zeta and eta is equal to the field which is incident on the object which is u naught of zeta and eta, and the input object has the transmittance which is amplitude transmittance which is Ta of zeta and eta. So substituting the values of u naught zeta and eta over here, the full expression, and the substituting the value of Ta of zeta and eta which is equal to capital A only, our expression becomes equal to this one which is given in equation number 53. So the field u naught prime of zeta and eta, which is the field just after the input object, will propagate further towards the right along the z axis and will be denoted by uf of u comma v at the Fourier plane. That is, we have now calculated the field just after this zeta and eta plane, and you know that that field has to travel a distance d so that it can reach the Fourier plane. So you see that we have next to calculate this transformation so that we can calculate the field at the Fourier plane. We have to express u of u and v in terms of u naught prime of zeta and eta using Fresnel diffraction formula, but subject to the following changes. You can read these changes by yourself, but I am going directly to the figure number 55. But you know that the distance d over there, as I have shown you just a minute ago, that d must satisfy the equations, the conditions given in equation number 55, so enabling us to apply the Fresnel formula. So for the Fresnel diffraction formula to hold in this region, that is in the region D, that is in the region after the input object and the Fourier plane, it must satisfy the following condition. D must satisfy these two conditions. That is the absolute, that is the maximum of the absolute value of u minus zeta divided by d should be less than 1, and also the maximum value of the absolute value of v minus eta divided by d should be less than 1. So this is equation number 55. The transformed Fresnel formula is given now below as in equation number 56. So you see that now we have given this formula, which is the Fresnel formula in its expanded form, and you know that in the curly bracket we have u naught prime. This is the field just after the object as a function of zeta and eta, and you know that there are two quadratic phase factors appearing. One is at the input plane, which is containing zeta square plus eta square, and the other factor, the other quadratic factor, which is outside the integral, contains u square and v square, which is associated with the Fourier plane variable. So you know that in the integral there is n exponential, which is e to the power minus iota 2 pi over lambda d, and within the parenthesis we have u zeta plus v eta. Actually this is the exponential that appears in the definition of the Fourier transform integral. So you see that the explanation of 56 equation number is complete. Now what we have to do is that we have to substitute the value of u naught prime as a function of zeta and eta, which we calculated in equation number 53, and now we are substituting, which is shown in red in this equation below. So red is actually the field that we are substituting in equation number 56, which is u naught of zeta and eta. So after substituting this, we have shown over here. So you see that, look at the first step, there are two quadratic factors within the curly bracket. One is shown in the red, which is e to the power minus iota k over 2d multiplied by zeta square plus eta square, and another factor which is in black is also contained within the curly bracket, which is e to the power iota k over 2d multiplied by zeta square and eta square. These two phase factors will cancel out, so we shall not have any quadratic phase factor within the curly bracket. So you know that now we are writing these in greater detail over there. We have taken a over f into d outside the integral as we have shown in the red, and you know that we have left within the curly bracket only two terms, that is, one is the pupil function and the other is the amplitude transmittance as the function of zeta and eta, and of course this is the Fourier integral. And you know that here you will notice that p is also dependent upon the zeta and eta coordinates. Okay, now let's proceed further, and you see that we can write this equation with this integral can be written as, because it is the Fourier transform of pupil function as a with coordinates zeta into f over d comma eta into f over d, and then multiplied by the t8 amplitude transmittance of the input object as a function of zeta and eta. So now we can write the previous equation symbolically as the Fourier transform of the product of these two functions, and which we have also written in the second step of equation number 57 in words, that is some exponentials before that one multiplied by the Fourier transform of the part of the object under illumination, because this is not the Fourier transform of the whole object, but due to the application, due to the multiplication of the pupil function, we have used a word that this is the Fourier transform of the part of the object under illumination, not the full object but the part of the object. Okay, now the related intensity can be calculated by multiplying by uf by its complex conjugate, and you know that this is simple, which we have shown in equation number 58. Okay, so this is over. So 57 and 58 respectively gives you the field at the Fourier plane and the intensity at the Fourier plane. Now you know that we can compare this equation number 58 with one of the equations that we calculated when the input object was placed in front of the lens by a distance d, and you know that here our object is placed behind the lens. So let's compare the similarities and dissimilarities between these two approaches. The fields in both cases are related to the Fourier transform of the part of the object under illumination. You can see in equation number 58 or in equation number 56 that we have the Fourier transform over there. So similarly in the previous steps, when the input object was also placed in front of the lens, we also encountered their Fourier transform expression. Quadratic phase curvature appear in both cases, though with different radii of curvature. So you see that this quadratic phase factor, as you can see in the field, we have the complex quadratic phase factor using containing the coordinates u and v, that is the coordinates of the Fourier plane, and you know that such a phase factor also appeared in the case when the input object was in front of the lens. But you know that those phase factors also contained some terms within that, and it was also possible to control the phase factor in the case when the input object was in front of the lens. But you know that in this case, that is in equation number 57, we cannot control this phase factor, we cannot eliminate this phase factor, so it will remain there. So the quadratic phase factors appear in both cases, though with the different radii of curvature. The quadratic phase term can be omitted when the input object is placed in front of the lens at its front focal plane. So you see that we can get rid of this quadratic phase factor containing u and v for the case when the input object was in front of the lens by using f is equal to d, or by using d is equal to f. Then such a phase factor can be eliminated completely. But you know that this possibility is not available for this equation, for this case. So same portion of the same size of the object is illuminated irrespective of the position of the object in front of the lens. However, the size of the object under illumination changes with the distance behind the lens. So you see that in the first case, when the object was in front of the lens, if you move that object closer or away from the lens, the size of the object which is being illuminated is not you know that changed. The size of the illumination remains constant for such an object. But you know that this object, in this case when the object is behind the lens, if you move that object closer or away from the lens, the illuminated portion of the object will change. The scale of the Fourier transform is controllable with the movement of the object behind the lens, but the movement of the object in front of the lens, the scale in front of the lens, the scale of the Fourier transform does not change. So you see that here, since the size of the object will also change, so the Fourier transform size will also change in this case, but the Fourier transform size will remain the same in the previous case when the input object was placed in front of the lens. So when the object placed in front of the lens is at a closer distance from the lens will intercept the greater part of the wave front diffracted by the input object. But when the object placed behind the lens is at a closer distance from the lens, the object will intercept a greater part of the wave front coming from the lens. So you see that this is the end of slide number 53.